this can be 3/4, right? And 1/4, and 1/4, right? Now we gave the identity matrix here, right? That means this matrix is the result of the same operation that we used to bring the matrix A to the identity matrix. In other words, this should be the inverse of A. Right? So that's the inverse of A. So A inverse is whatever it is. 1/4, 1/4, 1/4, and right? So it's called the row reduction method or the Gaussian elimination method for finding the inverse of the matrix. This method can also be used to find what I call the LU factorization. So we can also use the C method for finding LU factorization of a method. Probably it hasn't been too much for today. So, now we will discuss some applications of linear equation. For that I will use
with 5 minutes.
All right. That's very handy.
Luôn từ trong đó. Đấy, đúng rồi. Rồi.
Okay. Maybe you are interested in this problem. These are the nutrition facts of some type of food. And let's say if you want to be healthy, you want to eat a certain kind of food, right? So the first simple question here is, so how much of each type of food should we eat to get, for example, 32 grams of protein? Does anyone know the answer? Well, simple answer, right? So the proteins in ground pork is 16 grams per 112 grams of pork, right? Here is 23 grams in 113 grams of ground beef, and here is 21 grams in. Now, which type of food should we eat to get, let's say, 32 grams of protein? One simple answer is, okay, you just take, if you like pork, and just take to this, I mean 203 to 24 grams of pork, right? Right? So you get that number, the amount of protein you need, right? Or if you want a combination of beef and shrimp, then you may take, okay, how much? Let's say this takes 112 grams of shrimp and it gives 21 grams of protein, and the rest from beef, right? So now the second question is, so how much of each type of food should you eat to get, let's say, 32 grams of protein plus calories, let's say 500 calories, right? So the question is hard, right? But how should we answer this question? Does anyone know? Well, I think there's no easy answer to this question, but we should think about the way, the systematic way to solve it, right? So what should we solve it? How should we solve it? So let me just call X is the amount of pork, Y is the amount of beef, and Z is the amount of shrimp that is eat, right? So let's say it is in gram. So we need we have two equations to solve, right? We have two equations. So for the protein, pork is what? X times, so each gram of pork has 16 over 112. This is the amount of protein in each gram of pork, right? Plus Y times 23, right? Over 113 plus Z times 21 over 112 equals 32, right? And then we set up another equation for the color rate. And that's the way how we solve, right? So X times color rate of 325 over 112 plus Y times 200, right? Over 113 plus Z times 170 over 112 equals 500, right? And as we see, this is a linear system. Linear system, right? So the linear systems can be used to solve diverse problems. If you are interested in this kind of problem, I can give you data. We can build a very good, very healthy meal, right? So think about tonight and make something very healthy for you, for the family. Yeah? Another application of linear systems is what I call the Leontief input-output model in economics. We know that linear algebra has many applications in math. So we use linear algebra to solve differential equations, partial differential equations. But in 1945, the U.S. economist, his name is Leontief, and he tried to solve a system of 42 equations with 42 unknowns. I think it's not a big problem nowadays, right? You put it on a computer and it gives you the solution in a few seconds. Right? But at that time, it took him a few months to solve the problem, to program and then to solve the system. But it's worth it because he later got a Nobel Prize for this work on this model. It's the same thing that he did. So what is this model? In his model, Leontief divided the U.S. economy into 500 segments. For example, the agriculture, manufacturers, services, a lot of types of services, yeah? Like heavy industry, light industry, and so on. So and he separates the whole economy into 500 sectors, 500 different sectors. And the question he wanted to answer here the question he wanted to answer is, so what is the production level? So how much of each type of product we should produce to match the demand? So probably we don't want to produce too much, right? But we don't also want to produce too little, right? So we want to match the production level and the demand, right? So that the economy is in a healthy state. Well, in this lecture, let me just give you a simple example. So here is even more simplified version, right? So we just have three sectors: manufacturing, agriculture, and services. Now, what is this table tell us? It tells us the amount of each product needed to produce other products. So for example, if you in the service here, to produce 1 unit of service, we need, let's say, 0.5 unit of manufacturing and 0.3 unit of agriculture. Right? Or in agriculture, to produce 1 unit of agriculture, we have to use like 0.2 units of agriculture, 0.3 units of manufacturing, and 0.3 units from agriculture, and 0.1 unit of service, right? To produce the 1 unit of agriculture, right? And similarly, right? But of course, if all the products are consumed by this, then nothing's left for us, right? Or we want something more, right? So there's another sector, what we call the open sector, or what I call the final demand. So this final demand determines how much of the product we should produce. Right? So in this example, So let's try to determine the production levels. I mean, how many units of manufacturing, agriculture, and services we should produce in order to make the final demand of 50 units of manufacturing, 30 units of agriculture, and 20 units for the services. Right? So what are left? So after the products are used by each other here, other sectors, we can still have 50 units from manufacturing, 30 from agriculture, and 20 from the services. So how do we solve this problem? Are there any ideas on this problem? Even a wrong idea is also good. So let this code act as the production factor. That means the vector of all the number of units produced by each sector, right? At each sector, right? So actually it has three components. The first one is for, let's say, manufacturing, the second one is for agriculture, and the last one is for services. Right? So we want to have 50 product labs for manufacturing, right? From a manufacturer, 50, right? And then we want to have 30 unit labs for agriculture and 20 for services, right? So this is what this is the demand, the defined demand we want to have. Now, this is the amount that is produced, right? That is produced. There's a total production level. But among this number of units, some of them are consumed by other factors, or even itself by the same sector or by other sectors, right? Here's that. So here's 0.5, 0.3, 0.2, 0.2, 0.3, 0.1, and 0.1, 0.1, and 0.3. Alright, so let's say 50% of X needed for the 50% of X but okay, we don't need that anymore. So let's say 50% of X is used by manufacturing, and then 30% of agriculture is used, and 20% of services is used. Right? So the first equation will look like this: X1 is the number of units produced for manufacturing, right? And X1 times 0.5 plus 2 times 0.3 plus 3, 0.2 equals 50, right? What is it? So this is the total production level of manufacturing. So the final demand of the manufacturing here, 50% of this, of X1, is used by manufacturing itself, right? Let's say we produce steel, and the steel is used to produce to make houses, right? And 30% of X2, so 30% of agriculture is used to produce manufacturing goods, right? And then 20% services is used to produce the manufacturing goods, right? And so on. And then we get this system. It's not a big deal to solve this system. By solving this system, we have actually models. Let me see. I think I did a computation already. It's about 194, 108, and 72. So this is the amount of manufacturing, the amount of agriculture, and the amount of services that we should produce in order to make this final demand, right? To make this final demand. Here I already wrote out the number. Yeah, so that is the some applications of linear systems. There are many other applications of linear systems. I don't think we should discuss too much today. So I will stop now. Now it's time for the questions. Yeah.
Ai còn có hỏi gì không?
Did you get a similar answer? Maybe my answer was wrong. Okay, so let's see. What kind of questions do you have?
When you teach linear algebra, what's the role of the computer to support to teach the x, because it is not enough time to teach the solution from the algorithm of LSC. So we have to use computer or use the software to support.
Well, the main idea in the lecture is to give a big picture, to give a picture. It's not just to focus on computation. Yeah. So usually you take simple examples to illustrate the methods. Let's say the row deduction method, or you can call Gauss elimination method. So we use simple examples, like usually 2 by 2, 3 by 3, or 4 by 4 matrices. For larger systems, yeah, we usually we use MATLAB or Mathematica. Those are simple, let's say, computer algebraic systems are used for doing the computation for us. Students can check. Students can use those software to check the answers. But the main idea of the lecture is to give the big picture. It's not focusing on the computation. See the big picture is harder than doing the computation. And we try to give many, let's say, useful information about application. There are several applications you can discuss using linear algebra. So, for example, the application in solving differential equations, partial differential equations, if it's for the math, in those problems, in computer graphics, in encoding, decoding, and what else? In control theory. So in many areas of application that we can discuss here. Using linear algebra. Actually, linear algebra is considered as the central of math. One of the central topics of math. When we solve linear, when we solve different equations, we also need linear algebra. In optimization, we definitely need linear algebra.
So you touch a lot of application of the linear system. So which resources or what resources to help you or help teacher to take the application of the many areas in the life?
Well,
Center for math.
Yeah.
Resources.
Yeah, usually we choose textbooks like that. Examples are usually included in the textbook.
Textbook.
Yeah. And there are many other textbooks, not only one, but many different textbooks that we use. So sometimes you pick some problems from one textbook and other problems from other textbooks. But usually, when writing textbook for undergraduate students, authors usually try to mention applications to motivate students to learn, because not many students like math.
Yeah.
So yeah, we try to motivate them. So why we learn linear algebra, why we learn math. I remember some years ago, in a discussion in the Hanoi University of Science, one of the professors told us when I was a student, there was I remember one student asked a question, so what is the use of math? Why do we learn math? So he said that learning math is like trying to catch a dragon. So we teach students the methods to try to catch a dragon, and then our students will teach our next generations to catch the same methods to catch dragons. It seems, well, at that time I thought, oh, it could be true, because I didn't see any use of math in real life. So it's like, oh, this is like a big game, big brainstorming game. But actually, it's not true. Probably we do not use that much math here, but I work with many engineering researchers, professors, and they use a lot of math. and yeah, they are even better in math than mathematics because they need to use a lot of math. So one of the applications that I have worked on is to see through dress. Do you understand what I mean? So for example, if you hide something under the clothes, we can detect, we can see it. So we're going to see through dress or see through wall, then we can see the structure behind this wall. Right? Or we can see underground, right? We look at underground. And that is not something like, it's not a game, it's a reality. We already did it, we did experiments. We tried to find landmines. You know landmines? We see a lot of landmines in our country. So we use, let's say here's the ground, and there are objects under the ground, and we send some signal into the ground and measure the signal, the reflected signal, and we try to determine this. Not only to determine this, but to characterize, to identify, means to see whether this is a rock, so let's forget it, or this is a mark. So we have to pick it up, right?
Cool. So in mathematics education, teachers should make students believe in their learning mathematics. So you have to collect a lot of situation of application, and it is a good experience. It's a good job. But there is a difficult in this. If you want to use mathematics in your life, you have to transform the your life situation into the mathematics situation. And I think it's not easy for a student to make it. And maybe you have to hack students transform, or you write, or you say the method directly.
It depends. Usually, well, of course, let's say the projects that students work on are not really a very realistic project. So we just have to work on like somehow a simplified version of the real life problem. Because even we cannot solve, or we may not be able to solve all real life problems ourselves, not the student, even the whole community. So many problems are still open for the whole community, for all the researchers, scientists. But as a student, you want to give them some simple ideas about like application problems. And then usually it's their choice. If they want to follow they can dig further. But usually we just discuss simple cases. Like in the Leontiev model, he used like 500 seconds, right? But in class, we cannot discuss a 500 by 500 model. So we only just consider a simplified model. But the idea is the same. If they understand a simple model, they should be able to understand the bigger model. But of course, they don't have to solve the bigger model. Those models I have already solved. But the idea is to have them learn how useful math is. So we can use math in many areas.
to